Alrighty, howdy folks. Let's move on to chapter 2, section 5. We are continuing with the cash flow diagrams. And like I said, we started with a single cash flow, and then we dealt with multiple cash flows. So far, we looked at two different kinds of multiple cash flows. The first one was irregular uh, cash flow in the sense you deposited money at some point of time, you pulled out money at some other point of time, and you did that many different times, and there is no rhyme or rhythm to it. And then last time we looked at uniform series, okay? And there were two kinds, the regular uniform series and a delayed uniform series. Now we'll extend this a little and we'll go to something called gradient series. This is also a multiple cash flow. What is this all about? Well, this is about a cash flow that kind of looks like this. What's up with this? Mm, I have to tell you something. Just before I started this presentation, when I looked at my PowerPoint, just so that I can prepare for it, I noticed that I didn't have this slanted line. All I had was these arrows. The thing about if about having just those arrows to indicate this is if I were to ask, hey, where is this thing starting? And quite understandably, you would say it's starting at 2, man, right? Because the starting arrow is at 2. But the truth is, this thing will not work if this is how should I put it? That is not what the idea is. It's not starting at 2. There is an arrow at t equals 1 whose height happens to be 0. See? So the whole thing works based on that. And so I said, nah, let me change this. And I put this single line, slant line. And I think it adds so much more clarity. Okay, cool. Anyways, gradient. Do you remember what gradient means back in calculus? Just change. Something, there is a slope. It's like a ramp. Suppose your deposits or withdrawals are like this. Now, can you find the present and future values of something like this? That's what we are about to do in this section. Cool. Once again, do you agree that in the moment we have done this many times? That's why I'm thinking the moment you see something like this for the first time, even if you don't know a nice, concise formula for it, as a concept, you should know exactly what to do, right? To find the present value for a cash flow like this. What do you do? Like we said many times before, take this guy, project him back to 0. Take the second guy and project him back to 0. So take every one of them and project it back to 0 and add them up, right? Is that strategy going to change now? No, it's exactly the same strategy, okay? So, all right, so let's do that. When I do that, g times, because it's 2 years projecting backwards, I need to multiply 1 plus I raised to negative 2. And 2g raised to negative 3, right? So 2g times 1 plus I raised to negative 3 and so on. So now the question becomes, whoa, wait a minute. Is there a nice formula to figure out the sum of something finite series like this? There is, but we need to do some math. Now, textbook people will just simply give you a formula. And when you for this series, this is the formula to find P. I don't know. I feel that is cheating. I feel that both you and I are perfectly capable of just doing a little math and figuring out these kinds of things for our on our own. Do you need to figure out? No, not necessarily, but it would be a nice intellectual challenge if we do, right? That's the point I'm trying to make. Okay, cool. Let's move on. To find the sum of the finite, we'll do some math. What's the math we're looking at? If I asked you, hey, what's the sum of 1 plus 2x plus 3x squared plus 4x cubed plus dot dot dot, so on, plus nx to the n minus 1? The truth is, I don't know either. However, what I do know is if we had x plus x squared plus x cubed plus so on up to all the way up to x sub x to the n, that I know what the formula for the sum of that is. Oh, how? Well, it's a simple geometric series. Would you agree that each time we are multiplying by x to get the next term, we start with an x, multiply that by x to get the second term, you get x squared, multiply x squared by x, you get x cubed. Aha! So that is the pattern of a geometric series, and it happens to start at x and end at n, x to the n, right? So again, a times r to the n minus 1 over r minus 1. That was the formula. A is the first term x. R happens to be x. So x to the n minus 1 over x minus 1. Ta-da! Yeah, this is the good old, I use that formula. A times r to the n minus 1 over r minus 1 with a being x and r also being equal to x. Cool. Now, check this out. My jaw just dropped when I looked at how people find the sum of this. Recognize our original intention is to find the sum of this. And when they started with this, I'm like, yeah, okay, yeah, so what? And then when they did this manipulation, I'm like, oh, dang, this is awesome, man. So pause and see if you can think of how to go from the sum of this to the sum of this. Can you figure out? If you can, then you really should pat yourself on the back. Cool. Okay. The way they did that is, wait a minute. What's the derivative of x? 1. What's the derivative of x squared? 2x. Of x cubed? 3x squared. Uh-oh. Could we just simply take the derivative of the left-hand side and set that equal to the derivative of the right-hand side? Yeah, that is perfectly possible. If f of x equals g of x, then the derivative of f of x equals derivative of g of x. Guaranteed. That's all there is to it, right? Dang, I was like, that is pretty impressive. So the derivative of x plus x squared blah 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 is 1 plus 2x plus all of this. And now the only question is, do we know how to take the derivative of this complicated thing? Quotient rule. Lodi ham minus haddy low over low low, right? What? Low is the denominator, high is the numerator, d means derivative. Low d high. Denominator times the derivative of the numerator, low d high, minus high d low, minus numerator times the derivative of the denominator, over low low, the square of the denominator. So if you apply that, now this, I'm not going to go over all the details of how I differentiated. I expect you to look at it, pause the video and do it yourself and convince yourself that whatever I did, all these steps are perfectly fine. They are. So what did we find? We know how to find the sum of 1 plus 2x plus 3x squared plus all the way up to nx to the n minus 1 to be this big long thing. Cool? Why? What? Why do we need this? That is because look at what we have here. Something, 2 times something to the this, 3 times negative 4, right? So it seems to have a similar pattern. But before we jump, I thought it would be good to ask this question first. Y to the negative 2 plus 2y to the negative 3 plus 3y to the negative 4 and so on, all the way up to, instead of n, I'm just using a mu. There is no big, I guess I'm trying to show off. Hey, look, I know how Greek letters work. So mu minus 1 y raised to negative mu. Please don't let that bother you too much. Something like m minus 1 times y to the negative m. That's all there is to it. So for that, I notice that once again, I can factor out a y to the negative 2. And if I do that, this is what I end up getting inside. Okay? The term in the square brackets has the exact same form, as what we did before. 1 plus 2x plus 3x squared plus 4x cubed plus so on, all the way up to nx to the n minus 1. Would you agree with me with that? The stuff in the square brackets, this guy, 1, 1, yeah, plus 2x, whereas we have a 2y to the negative 1. Are you telling me that x equals y to the negative 1? So y to the negative 1 is the playing the role of x? At least based on a comparison of these two terms, that's what it looks like. And let's continue to see if that is the case. X square should therefore be y to the negative 1, the quantity square. That is y to the negative 2, 3y to the negative 2. So it is 3y to the negative 2. Good. So now at least we know that the role of x is being played by y to the negative 1. So wherever we see x in this formula, we'll replace it with a y to the negative 1. Cool. All right. What else do we need to look at? We have nx to the n minus 1, right? Nx to the n minus 1. So what is n? Would you agree n must be mu minus 1? Right? So if x equals y to the negative 1 and n equals mu minus 1, that is the substitution we need to make. If we do simply that, we got the sum of this. So y to the negative 2 and all of that stuff is y to the negative 2, which I factored out. And for the stuff inside the square brackets, applying what we just talked about, the similarity between the two equations, this is what we would have. 1 minus n plus 1. N plus 1 is simply mu, so that's why I have a mu. X to the n, x is y to the negative 1, y to the negative 1 raised to n, but n itself is mu minus 1. So y to the negative of mu minus 1, right? Y to the negative n, but n is mu minus 1, so y to the negative of mu minus 1. Cool. Plus n is mu minus 1. X to the n plus 1 is y to the negative of n plus 1, but n plus 1 is mu, so this is y to the negative mu. Cool. All I'm doing is plugging these values wherever I see an x, and wherever I see an x, I'm plugging y to the negative 1, and wherever I'm seeing n, I'm plugging mu minus 1 and simplifying it. Cool. And this is what we get. Now, let's simplify this once again a little more. For instance, both the top and the bottom will multiply by y to the mu. If we do, we get y to the mu times 1 is y to the mu, and this becomes minus mu times y to the negative mu, y to the mu times y to the negative of mu minus 1. If you do a to the m times a to the n is a to the m plus n, that reduces to a simple y. Plus this becomes a mu minus 1 because we are multiplying by y to the mu. Y to the mu times y to the negative mu is just 1. because y to the mu over y to the mu, which is 1. Cool. All right. Now, y to the negative 1 itself is 1 over y, right? Where did this y to the mu come from, man, in the denominator? I told you we are multiplying both the top and the bottom. So in the bottom, stands to reason there would be a y to the mu. That's all that's all this is. Okay, this is 1 over y minus 1, and that is being squared. Cool. This part, the 1 over y minus 1. If I did the subtraction, would you agree you would get 1 minus y all over y? 1 minus y on the top over y in the bottom? Cool. So this that so 1 minus y, the quantity square, because this is being squared, over y square becomes times positive y square, 1 over y square, 1 over y square becomes y square, and that y square times this y to the negative 2 is just 1. So that's why this simplifies to y to the mu minus mu y plus mu minus 1 over this y to the mu times 1 minus y, the 1 minus y, that quantity, 1 minus y squared. Okay, oof. All right, so now we know the sum of y to the negative 2 plus 2y to the negative 3 and all of that stuff we know. And this is what we're going to apply to our thing. When we have this, the present value is this, what we said. Now, if I factor out a g from every one of them, would you agree that the stuff inside the square brackets is looking like y to the negative 2 plus 2y to the negative 3 plus 3y to the negative 4 and so on, all the way up to mu minus 1 y to the negative mu, right? And we know the formula. So once you know that, what is y? That's the key. The role of y is being played by 1 plus I. So that's why I'm saying 1 plus I. Y to the negative mu, the very last term is mu minus 1, y to the negative mu. The very last term here is n minus 1 times 1 plus I to the negative n. So that means mu minus 1 must be equal to n minus 1, which means mu must be n. And that is also confirmed by what the exponent is. Exponent is negative mu, exponent is negative n. So negative mu must be equal to negative n, so mu must be equal to n. That's what I'm saying. Cool? All right. And then if you plug and chug and simplify, this is what it becomes. Okay? Or I like this particular form. Take a good look at this one. Writing P, the present value of this uniform gradient, the gradient series is this way is, if you recall, for the uniform series, the formula looked like this: A times, instead of G, we had an A. We still had the same 1 plus I to the n, but we had a minus 1. That is a small change. Here we have a minus the quantity ni plus 1, whereas for a uniform series, the top would be minus 1. There is no minus ni in it. And in the uniform series, we will still have the same 1 plus I to the n. The only difference is we will have an I, not an I square, right? So that is the small change. There's an extra I multiplying in the bottom, and there's a ni that is being subtracted on the top. That is the only difference between when you observe, how in the world do I memorize these things, man? Whether you need to memorize or not is a different story. Quite possibly in your exam, you'll be given a sheet with all these formulas. But instead of relying on the formula every time, if you can draw it from memory, that is so much better. Okay, there are advantages to it. Anyways, so we'll find the future value f for the pure arithmetic gradient series. So we know the present value. We'll try to find the future value. Do you know what to do? I think by now you should, right? If you know the present value and you need to find the future value, all you need to do is take the present value and project it forward by n number of years. And we also know that to do that, all we need to do is multiply the present value by 1 plus I, the quantity raised to n. And that's exactly what we are going to do. We take this guy and the future value is nothing but the present value times 1 plus I to the n, where p is this guy. And so future value is this times 1 plus I to the n. Just simply becomes this. The future value for the uniform arithmetic series was a times 1 plus I to the n minus 1. There was no minus ni. And in the bottom we had a I. And here we have an I square and a minus ni on the top. That's the difference. Cool. With that, let's move on to some problems. Oh, we'll now combine. What if you had an uniform series? I better be careful. This is kind of important. So we have uniform series A starting at 1. And we have a gradient series starting at what? Is the gradient series starting at 1 or 2? The gradient series is starting at 1. It just so happens that it is 0g at t equals 1. Right? Again, recall that ramp that we had set up. Okay, so g, 2g, n minus 2g, and n minus 1g. By the way, why is this n minus 1g? How in the world did I know to make that to be n minus 1 times g? Why is it not ng? Right? Look at the pattern. At 2, we have a 1g. At 3, we have a 2g. Right? At 3, we have a 2. At 4, we have a 3. So would you agree? N, we should have a n minus 1. As simple as that. Pattern recognition. Okay. All right. All we need to do is take this guy's stuff, present value, the uniform guy, and then add to that the gradient guy. As simple as that. Okay. There is no real, what do you call, intellectually complicated concept behind this at all. Cool. John deposits $3,000 at the beginning of year 1, and for 4 more years he deposits an extra $1,000 to the previous year's deposit. What is the present value and future value at t equals 5? Take I equals 8% per year compounded annually. Deposits 3,000 at the beginning of year 1. Okay. And for 4 more years, he deposits an extra 1,000 to the previous year's deposit. So year 1, ladies and gentlemen, what did John deposit? 3,000. Year 2, 3,000 plus 1,000, right? An extra 1,000. Oh, you mean 4,000? Yes. How about year 3? Add an extra 1,000 to the 4,000, 5,000, 6,000. That is what he did, right? So the CFD looks like this. A, this is 3,000 at the beginning of year 1. Yeah. And then each time he is adding 1,000 more. So to this 3,000, he adds 1,000. Then he adds 1,000 to this guy, which is the same as adding 2,000 to the A, right? 3,000 plus 2 1,000s and 3 1,000s plus 4 1,000s. So this is that $1,000 thing. That is the gradient G in this case. So here is a combination of both. A is 3,000. G, right, that extra money he's adding is $1,000. I happens to be 8% or 0.08 and N is 5. Cool. Can we find, what are we supposed to find? What is the present value at t equal to 0? So the formula for present value for this one, a times 1 plus I to the n minus 1 over I times 1 plus I to the n. I think, yeah, I'm glad that this problem we are juxtaposing both the uniform and the gradient right next to each other so that we can see. Instead of a we have a g. Instead of minus 1 we have a minus ni plus 1. Instead of I we have an I square. Right? Everything else is the same. Okay, plug and chug, and turns out to be $19,350. That is the present value of these deposits. Cool? All right. If you want to find the future value of this, fairly straightforward. Take this guy and project it to the future by 5 to t equals 5. So 1 plus I, the quantity raised to 5. Do that and you are in business. So the future value of all these deposits is $28,432.34. Cool? All right, let's move on to the next one. You want to be able to withdraw from a savings account $800 at the end of year 1, 900 at the end of year 2, 1,000 at the end of year 3, and so on over a total of 5 years. How much money must be on deposit right now at the year end of 0 to just deplete the account after the 5 withdrawals if interest is 5% compounded annually? I don't know. This is the same, similar stuff. A is 800. You want to be able to withdraw 800. Then each time you are doing, I guess, okay, 800, 900, 1,000, 1,100, and so on, right? So there you need to clearly understand that A is 800 and G is that extra money. 900 minus 800 is 100. And this 1,000 is 2 times 100, right? 1 times 100 is the deposit at end of year 2. And 2 times 100 is the extra deposit. 3 times 100 and so on. So G is 100. Plug and chug. You get this amount. That is the present value of these deposits. Okay. What is the uniform series equivalent of the arithmetic gradient series shown below? That's an interesting one. Can you figure out what the question is asking about? What is the uniform series equivalent of the arithmetic gradient series shown below? Any idea? If you need to pause the video, go ahead and do that and kind of try to answer it for yourself. Okay. So, instead of depositing this arithmetic gradient, what if I want the value to be exactly the same? I want another way of accomplishing the same thing. But the second way is where I don't make payments like G2G and blah blah. Instead, I make uniform payments A. So what should that A be so that it is exactly the same as doing this stuff here that we are doing here? That's what the problem is about. Oh, you can find that? Yeah, you can. How? Well, Find the present worth of this distribution as well as the uniform distribution. They both must be equal. What did you say? Present worth should be equal. Why not future worth, man? At n. Yeah, be my guest. It's the same interest rate. So you can look at the present value of both the distributions or the future value of both the distributions. Either way is perfectly fine. So that's what we will do. So here I have the present worth using the uniform series that should be equal to the present worth of the gradient series. Cool? And now it's just a matter of what should A be? Can you solve for A? Algebra. A equals, okay, boys and girls, multiply both sides by the reciprocal of whatever A is being multiplied by on the left-hand side, right? Divide by this, or divide by the coefficient of A, or multiply by the reciprocal of this. And that's exactly what I'm doing. Notice I times 1 plus I to the n, what was in the denominator came up to top. 1 plus I to the n minus 1 over here came down to the bottom. Cool. Now, would you agree 1 plus I to the n and 1 plus I to the n cancel? I over I square becomes 1 over I. That's it. So, becomes this. You don't need to memorize this formula, but it would be a good idea to memorize these two so that you can derive it yourself. All right. There we go. Whoa, that's it. Yeah, I think some silly problems you can always do some silly problems, but the concept is this. And in fact, we will do some real world applications. That's what eventually we will be doing. Okay. Alrighty. That's it, folks.